Okay, so we are 1 minute away, people. I will present also myself. I'm Estefania Gonzalez. I am one of the members of Inveniam Group, and we are part of the communication team of AIRE. With me, we have Laia, which is also one of the team members of AIRE, and from Inveniam. We have a lot of people already in, so that's good. I hope everything sounds good. Beatriz, you can share a screen, right? You already tried it. Perfect.
Yes, and can you hear me?
Yes.
Okay. Sorry, I'm in an airport, so maybe you can hear some background noise, but I hope that
it sounds really
everything's
good.
okay.
Sounds really
I have my headphones. Okay, I will start when you tell me, Estefania.
I think we can start. It's already 3. So, like, just a brief introduction for the ones who might have joined in the last 5 minutes. Welcome to our first webinar of AIRE Project. I am Estefania. This is Laia and Beatriz. Beatriz is the project coordinator of AIRE Project from CENER, and she's going to kick off this amazing webinar.
Okay, so hello, thank you, Estefania. Welcome everybody to this webinar. As Estefania said, we are very excited because this is the first one. So we hope that we will have like many webinars explaining all the job that we are doing in AIRE. So first of all, I'm Beatriz Méndez. I'm the AIRE Project Coordinator. I'm part of CENER, that is the Spanish Renewable Energy Center. So I'm going to make a brief overview of the project, very, very brief. And then I will give the floor to the experts that are going to talk about the different experimental campaigns that we are already doing inside the project. After that, you will have a Q&A and question and answers session that will be managed by Estefania, Laia, and my colleague Oscar, because I have to leave. I'm so sorry about that, but I have to leave. So I will start my presentation. AIRE is an European project funding under the Horizon Europe program. It started in this year, in January. So we are almost finishing the first year of the project. It's an European partnership. We have 10 partners, and the budget is more or less 6 million euros. So the main objective of AIRE is to understand how site location and climate conditions affect wind turbine and wind farm operation and design. So in AIRE, we are making an holistic approach in order to study the effect that variables such as precipitation and dust have on the wind turbines and wind farm operation, because we never include precipitation, for instance, on dust in our models or tools. We will also improve wind turbine and wind farm design and control. And finally, the objective will be to increase wind energy efficiency. So the idea in AIRE is to study, as I said, climatic conditions different from the standard ones. We are going to include precipitation and dust in our studies. We will include the site characteristics because wind energy is deployed in many different sites. So we are going to also include that characteristics. And then we will move to study all our advancements in the wind farm level, wind turbine level, and especially we are going to check the effect on component durability, especially on blade erosion. The main AIRE impacts will be reduce the levelized cost of energy, increase annual energy production, and reduce operation and maintainability of wind farms and wind turbines. Our consortium is made of 10 partners, as I said before. CENER is the project coordinator. Then we have 2 very important wind farm owners that are Capital Energy and Engie. We also have an OEM, Siemens Gamesa, and we have 3 different research institutes such as Fraunhofer in Germany, VTT in Finland, and Catapult in UK. We also have DTU, an university, and PLOCAN, that is experimental site in the Canary Islands. And also we have Inveniam, that are in charge of the communication and dissemination activities inside AIRE. One of the most important parts of AIRE are our sites. When we created this project, we decided to cover a wide range of different situations in order to study different terrains, different climatic conditions. So our sites are made of these 8 sites that are shown in this slide. We have 2 different types, experimental sites and also industrial wind farms in operation. So we have 3 wind farms from ENGIE, 1 offshore, 1 high altitude terrain, and another 1 complex terrain in the North Sea, in the North Sea, in France, and in Italy. Then we have 2 more offshore sites in Levenmouth, Patapul, and in Riso campus, with 2 different wind turbines, a big 7 megawatts wind turbine and a small wind turbine in Riso campus. And then we will complete this set with the experimental site of Alaiz, that is a complete terrain site that belongs to CENER. We also have a PLOCAN, that is the experimental site that is in the south of the Canary Islands. Sorry, I have to stop because I'm not sure if you can hear me. Estefania, can you confirm?
Yes, we can hear you. We
Okay,
barely hear
because
the
I have
person behind you.
this.
Yeah,
Okay.
we can hear
Okay.
her, but yeah, like
Okay.
really behind.
Okay. So sorry, I'm in an airport, as I said before. So now the English version. So okay, so I was saying that we have Alaiz, that is a complete terrain with very high altitude. That is the experimental site from CENER, and that is going to be presented afterwards. We also have in the AIRE side Las Tareas wind farm that belongs to Capital Energy. And then we have PLOCAN, that is a very interesting site because it is an offshore site, but in a subtropical climate, operating the wind turbine in conditions with very high levels of sun and dust present in the air. So we are going to gather a lot of information in these sites that will be the principal part of our project. So this flower is the concept, represents the concepts of AIRE project. So first of all, what we are going to do is to create open access knowledge hub with all the data that we are gathering in the experimental sites. Okay, with this data that we are going to explain afterwards, we are going to create 5 different models. The first one is a mesoscale model in which we are going to change the parameterization in order to include precipitation and blade status in the model. Then we will create we are creating already a wake and wind farm models, including also precipitation and sun in the effect on the models. Then we will move to the blade damage model, effort performance models, and finally, for the first time, we are creating a model already studying the 3D impeachment of the particles on a rotating wind turbine. With these models, we already started also to create 4 different tools. These tools are going to study very different aspects. The first one is the creation of an erosion risk atlas. Then the second tool will be an improvement on wind farm operation and control tool. Then tool 3 of AIRE project will be the wind turbine AP model prediction. And finally, the 4th tool that we are starting to develop now is the erosion safe mode operation tool. With all these tools and models, in a second step of the project, we will start in the second year of the project. We are going to apply them in 5 different case studies: offshore, onshore, high altitude, blind test to compare different tools, and then we are going to reevaluate the offshore case. And finally, with all these findings, we are going to design new airforce and new rotors, trying to use all the information that we gather, and in addition to create more durable and resistant airforce and rotor designs to the climate conditions. So the open access knowledge hub, that is the most important part of our project, and is the first one that we are creating, is made of the different information that we are gathering in the sites. It's part of the things that we are going to explain right after my presentation. So in these sites, it's important that you know that we are going to measure wind, precipitation, and sun present on the air current. Then we are going also to gather information about the wind turbine SCADA and blade status, making blade inspections, and then we are going to study and to gather the wind turbine SCADA data. And in all these sites, we are going to create this open access knowledge hub that will be made public. So if you are interested in this type of data, they will be made public at the end of the project to be used by other researchers and these industries. And that's more or less my presentation. So I will give the floor to the next speakers that, as I told you before, they're going to explain all the measurements that we are doing in the AIRE experimental sites, Alaiz, PLOCAN, DTU, and Orekatapul in Levenmouth. And that's all. I hope that you enjoy a lot this webinar. And yes, good luck.
Thank you very much, Beatriz, for your presentation. It's a great way of introducing the project. So for the next speaker, we will have Oscar Pires, which is also from CENER, and it's going to talk to us about the experimental campaign at Alaiz. Oscar, the floor is yours.
Hi. Good afternoon to everyone. Thanks for attending the meeting. Thanks a lot for Beatriz making the effort to have her presentation from the airport, just about to take her flight. And okay, so I will start presenting the experiments taking place at Alaiz, at CENER Alaiz experimental wind farm. And yes, and as Beatriz said, we will also have after me Ebba Dellwick from DTU, Iván Prada from PLOCAN, and Peter Kinsley from OREC, making also the presentation from their own sites. So I will share my presentation. Okay. Okay, I hope you can see the presentation. So I'll make this presentation about in particular the experiments and the measurements that we are taking at the experimental wind farm belonging to CENER at Alaiz. I will start just making a brief introduction of what CENER is, just in case if some of you don't know. And after that, I will just make also a brief explanation of the wind farm itself, and then I will then make a more detailed explanation of the measurements that we are taking for AIRE project. Okay, CENER is the National Renewable Energy Center of Spain, where we develop applied research and technology transfer for the industry, and we perform also testing and certification, and we do it in different areas. Wind energy, which is the department where I belong, but also photovoltaic solar energy, solar thermal energy, biomass, energy transition in cities, and finally a department of grid integration and electrical storage and hydrogen. CENER is the headquarters are located at Pamplona in the north of Spain at Navarra. The wind energy department where I belong, well, we do research at different areas of wind turbines, on the components itself, applying aerodynamic designs and consultancy and structural design. Also, we work on the wind turbine control, and not only in the wind turbine itself, but also at wind farm levels. And we also well, create different tools for analyzing the energy performance and the life cycle of components. We also have an important approach and development of offshore technologies, and we also have some lines of investigation on wind resource. The wind energy department of CENER have different infrastructures. We have a big wind turbine test laboratory, which is located at Sangüesa, close to, well, 30 kilometers from Pamplona. There we have blades structural testing and different other facilities. We have also a materials and process laboratory for investigating materials and components. And finally, we have the experimental wind farm, which I will describe later on. Well, CENER within the AIRE project is, as Beatriz mentioned, the coordinator. And a part of that, we participate in different activities as well. This experimental campaign at the wind farm for carrying data for the knowledge access hub. We also work on the wake and airfoil models and the tools for energy production estimation and wind farm control, and also in the also on the new airfoil and rotor designs the tasks that are taking place at the end of the project. Okay, now I will start already explaining the first, making a brief introduction of our experimental wind farm, the CENER experimental wind farm, which is located at Alaiz. This is also very close to CENER headquarters in the north of Spain at Navarra. This is a complex terrain wind farm, which is it's good to compare with other sites which could be in plain terrains or in offshore. Alaiz wind farm is at a height altitude of 1,120 meters. The winds that we can find there are in class 2. At 120 meters, we measure an average of 8.5 meters, so we are almost at class 1. And we have in this is experimental wind farm, so it is devoted to have prototypes from the manufacturers, and so they can install the new prototypes and have and test them and have and control the evolution of them. We have 6 positions for different 6 wind turbines. I have marked in this picture here, and the wind farm has 4 meteorological towers with 120 meters height, which are located as shown in the picture as well. Okay, now I will start talking about the experimental campaign that we are taking at Alaiz for the AIRE project. For this particular campaign, the main objective is to measure all the conditions of one of the wind turbines, the wind turbine that we have at position 5, which belongs to CENER. And we are taking data from the 2 met masts which are closest to this position. All the wind turbine is marked in the red circle, and the met masts are marked in the picture in the yellow circles. These measurements from wind farm are measurements that we already have, which are in our experimental wind farm, and we are using them for the project. And a part of that, we are taking rain measurements. For this, we have rented some particular equipment, which will be used to obtain mainly rain data that can be then compared with all the the data associated to the wind turbine. This additional equipment that we are using for the AIRE project are principally a micro rain radar that I will explain now how it works, and some additional equipment that will be a dysdrometer, a pluviometer, and a pyranometer that has been installed in the pyranometer has been installed in a met mast. Okay, now first I will start talking about the measurements from the wind farm, and these measurements come mainly from these two met masts. In both of them, we have the capability of measuring the wind speed measurements with cap anemometers and vertical anemometers at different height positions from 40 to 118 meters. And also we have wind vanes for the wind direction. And of course, we have also meteorological measurements with a thermohygrometer, barometer, a rain detector, and a pyranometer. This pyranometer is the one that we have installed now to help the correlation with the rain data. Okay, a part of that, of course, we are obtaining from the wind turbine SCADA the power information. All these measurements are taken at a rate of 20 Hertz, and the data is stored in statistical files of average of 1 minute and 10 minutes. So this is the information that we get from the wind farm itself. Concerning the rain measurements, what we have, as I mentioned before, is some specific equipment. This equipment has been installed as close as possible to the wind turbine where we are obtaining data. But due to the as this is a mountain and complex terrain, the closest plain area where we have been able to locate these equipments are close to one of the mast masts, the one which is marked here, and because it has a plain area, and of course we have put them as far away as possible from the met mast, so the met mast is not influencing on the measurements of this equipment. Okay, in this picture, in the picture below, you can see these three equipments, which consist on a micro rain radar, which I mentioned below, which is the main instrument that will allow us to measure different rain parameters. And the measurements from the micro rain radar will be helped with measurements from a dysdrometer and a pluviometer. Okay, I will explain more about this. The micro rain radar is mainly an instrument that sends up into the atmosphere a microwave signal and receives back receives back partially this signal depending on the precipitation in case there is rain or any precipitation like snow or any other type of precipitation. The signal is reflected back into the antenna, and it is processed, and it is able to to measure the raindrop size distribution, as well as the precipitation fall speed and rain intensity. And the good thing is that this is measured at the different heights from, well, you can start measuring from as low as 50 meters, and it can measure up to 3,200 meters. So we can obtain, well, precipitation information in all this range of altitude, which is very interesting. Of course, for AIRE project, we will be more focused, especially in the area from 50 meters to 400 meters, which will be the area or the height that is closest to the, well, to a wind turbine, no? Which is what it is more important to see how, because we are mainly trying to see how the rain is affecting different aspects of the wind turbine. This the data from the microrain radar is obtained at 0.2 Hertz. Now the disdrometer is measures something similar with a laser beam. It can detect the also raindrop size distribution, as well as precipitation fall speed, rain density, and also it can measure type of precipitation. Of course, this does only perform these measurements at ground level, no, just where the laser is applying. And the pluviometer is just a gain rate that measures average rainfall intensity. As I mentioned, this data is measured at ground level, but they give interesting data for correlating the data taken from the microrain radar. In the case of the disdrometer, the data is obtained at 1 data per minute, and the pluviometer data is averaged at 1 minute and also 10 minutes, so it can be correlated to the atmospheric data measured by the metmasts. Okay, so the important thing of the data that comes from the microrain radar is that it can be post-processed and analyzed to get the different rain parameters, and I am showing some examples here. No, we can, for instance, have the raindrop size distribution. In the plot that you can see here, you see that because the microrain radar measures at beams of 25 meters. So, for instance, we can measure at these selected altitudes of 100 meters, 125, 150, and well, whichever height that we are interested in. In a time scale, we can see the raindrop sizes in millimeters and how they are evolving with time. Apart of that, we can also see the precipitation fall slip, which is shown in this other plot, where we can see the time of evolution in the x-axis, and in the y-axis you can see the height, no, from zero. Well, not, it is not really zero. It's 50 meters. 50 meters, I said, to 3,020 meters, and we can see the different wind speed. The speed of the precipitation drops. We also can see in the same way rain intensity, and the good thing is that making a good post-process of the data, we can also obtain the different types of precipitation. We can see if we have rain or snow or drizzle, or well, we have the different types of precipitation that can be derived from the data, and when we can have that information also at different altitudes, which is also very interesting. Okay, just to conclude, I'll make an overview. And well, so far since the project started, we already began the first campaign of rain measurements. So we have already 10 months of rain measurements together with the meteo and the wind turbine data. We started the measurements at February of this year and up to now. So we have these 10 months of data where we have, as I mentioned, the rain data at different heights, wind speed also at lower heights, but some different heights, and also the meteo data from the metmasts. This data is already uploaded at the project repository, so it can already be starting to be used for other work packages and activities within the project. What is next? Well, we still have to perform final process of all the rain data that we have already measured. We are planning a new measurement campaign with micro rain radar together with a LIDAR, so we can have a more precise correlation of rain and wind measurements at different heights. We also are going to perform some wind turbine blade inspection, so we can also make a correlation between the blades state and different conditions. And finally, as Beatriz mentioned, all this data by the end of the project, which is also one of the most interesting things, will be openly accessed for everyone. Okay, so and this is everything from my side. Yeah, thank you very much.
Thank you very much, Oscar, for your presentation. It was really enlightening. The next participant would be Ebba. She's gonna talk us about the experimental campaign at Riso. So, Ebba, the floor is yours.
Good afternoon. Can you hear me well?
Yep.
Yeah. Great. Yes, I'm going to talk about what we are doing at within the AIRE project at the Riso site, which is one of the campuses of DTU in Denmark. So we're moving upwards or northwards from Spain. We're going to Denmark. And here to the right, you could see a map of Denmark, and we are not in the western part where DTU runs a couple of stations for testing wind turbines, large wind turbines, but instead we are at the Riso campus in central Zealand, where the red dot is. And here you can see a photo of our campus. Oh, sorry, this was not good. Just a sec. Here. So I am right now standing in the building where the arrow is pointing. We also have on the campus a small wind test turbine, a Vestas V52, and a mast in front of it. But our main activity in the AIRE project concerns the Riso mast, which you could see here. It's 122 meters tall. In addition to the mast, we have put a lot of instruments on a platform near the mast. So next, I'm just going to talk about how we measure precipitation, which is a key parameter in the AIRE project and can be used for validation of the simulations that will be made. So here is a photo of the platform next to the Riso tower. And this is what it looked like at the start of the project. And here is what it looked like this summer. And we have added quite a few sensors. So now I'll walk you through these sensors. Some of them are the same as Oscar talked about, so I can go through it quite quickly. We'll start in the very back where we have our oldest rain sensor. It's been operating, measuring here at campus since 1998. And we've always been a little nervous about how accurate it is. But you could see in the yellow text in the manual that it is sort of an instrument that can operate unattended for very long periods. So, but we haven't quite put our trust in just that. So we have done some calibrations. Yes, so here you could see that. What's good with that kind of a tipping bucket rain gauge is that it's very straightforward to operate. So here you can see a photo of myself when I was out calibrating it for the first time. So then it's very simple. We just put a known amount of water through the rain gauge and we see how much it measures. And then we see that we got an overestimations of up to 6%. And we thought this was pretty good for such an old measurement device. But we've also been a little uncertain about this technique. So then later on, we bought a calibration kit from the same manufacturer as the rain gauge. And we did the same thing again. And we're actually going to keep on doing this because we want to do it at different speeds and yeah, and maybe now in different weathers. But right now we would like to go out, but it's raining all the time, so it's hard to find a spot when we can go and not disturb the measurement series. But you could see here that we found a larger overestimation in the old rain gauge, so we know we could trust this data maybe within 10% only. Next on the platform, we have two laser optical disdrometers or present weather sensors. It's the TEAS laser precipitation monitor. Yeah, the TEAS is the manufacturer, and the Parseval 2 from OTT that you could see here. These are very, very advanced instruments. Basically, as Oscar mentioned, they measure via a laser beam when a raindrop passes between the emitter and the receiver. So then it records every droplet's size and speed. And from that, a number of other parameters are calculated, and every minute or every 20 seconds, depending on which instrument we talking about, it outputs about 1,000 values. So it's quite a complex instrument. Among other things, it outputs rain intensity at a very high temporal resolution, weather code, and droplet diameter and droplet velocity. And this is an example of what data from disdrometers can look like for 1 minute. So here we have the diameter on the x-axis and the velocity on the y-axis, and then you count the amount of droplets, and I've color-coded them here. And you could see it's the same minute, but the two instruments measures not quite the same number of drops and not quite the same velocities. So these are things that we are very interested in. Then we also had the micro rain radar MRR Pro from Metec, standing in the back here, and it works like this, as also Oscar said. It has an emitter that sort of, and there's a beam going into the parabola, and then it sort of shoots straight up vertically, and we look at the reflections. So this one I can go through very quickly because Oscar has already shown it. But here you could see the vertical velocity and the reflectivity of a rain event. And it's very super clear when it's raining and when it's raining a lot. So we have the same setting as in CENER, and we measure every 25 meters up to 3,200 meters. Yes. And I guess the good thing about this instrument is that it could give a wind park operator a warning. Since rain starts from the clouds, we would measure the rain before it would hit a wind park. So this is why this is a super good and relevant instrument in the wind energy context. So these were our rain instruments. Next, we go to the wind profile. And here you could see a photo of the Riso mast. It's a very accurate photo weather-wise, even if it's taken a couple of years ago. So in the mast, we have cap anemometers at 6 levels. The mast is 122 meters. And then the very top of the mast, we have a little balcony. And on that balcony, we do wind profiling with a wind cube V2. So in total, we have a measurement range of 370 meters together with a mast, and this measures since early February. And here you could see some example data where red is from the mast and blue is from the wind cube. And sometimes it looks exactly, well, somehow, sometimes it looks more as one would expect, and sometimes not at all. There's a lot going on above 122 meters height. I've looked at quite a number of profiles. Here is one, which is I think a little unusual. We have a strong shear in the bottom, and then from 150 meters above up to 270. It's almost no shear in the profile, and then we have shear again. And we see a lot of things like this in the data. So that's, I think, very exciting to be able to monitor these higher layers. Yeah, this is just a final profile from the mast where you could see maybe a more what one would expect kind of profile. The analysis at the Riso site has so far been focused on intercomparison of the rain sensors and sort of answering the question, how much does it really rain? And that's very complicated. I've also looked quite a bit at the availability of LiDAR data as a function of height. And more specifically, whether rain affects the availability. Now I'll show some results from the last question. Does rain affect the availability of LiDAR wind speed data? So here you could see a plot taken at 44 meters focus distance. So this is the first focus distance of the LiDAR at height 167 meters. And this plot shows the availability of the raw data. So how many sort of LiDAR pulses did we get good returns from within each 10 minutes? So 100% is, of course, a super good observation, and less is less good. So for the first focus distance, we have almost all the data at 100%, and here I've marked out those periods where it was raining, and they are also a very high availability. And then when we walk upwards, we see that we get more occurrences of lower availability, and also some when it is raining. But as a rule, the rain data is still staying at very high availabilities, above 80%. But then when we go to the furthest focus distance, it looks quite different. Yeah, so here we see all sorts of availabilities, and rain data sometimes coincides with very low availabilities, but it's maybe not a causation, but rather a correlation. I have looked at this also at slightly different rain thresholds, and then I could see that when I increase, say, the rain threshold, I see that the red dots drop down. So the tentative answer to this question so far is that sometimes rain seems to affect the availability of LiDAR wind speed data, but especially at large range. But when we look at how this translates to the overall availability at 10 minutes, so now I look at all the 10-minute periods. I have made some availability histograms also for that. And to the left, you could see that the percentage of 10-minute data that have more than 10% raw data availability, it remains really high also up to the furthest range. And this is what we usually see in Denmark. We have a lot of humidity in the air and good conditions for LiDAR. But if we say we only want those 10-minute data that have more than 90% raw data availability, then availability drops to below 50% at the furthest range. But overall, I think this is a very a positive result. Okay, so now I'm going to talk a little bit about the intercomparison of the range sensors. So we've studied some cases, and here you could see first that there are two things on the y-axis. One is rain intensity, that's the black curve and gray curves, and one is cumulative rain amount, which is the red curves. And here we see that over one day, we can get quite a big difference between the rain gauge and the one of the disdrometers. We actually see a 25% difference, which is larger than the uncertainty that we have seen in the calibration. So this points to that the disdrometer underestimates this rain event. Then we had a second case study where we looked at all three ground-based instruments and compared them. And there we see, and there I did another thing. I took both the standard output and then I also recalculated a rain rate based on the droplet, the recorded droplets. So I tried to kind of recreate the rain rate to understand how the instrument processes the data. So I get 4 curves and they agree quite nicely, but not completely. And that's quite interesting. So when I then look at the same, here I look at the cumulative rain amount for the 3 sensors, I also see differences. I see differences in the standard output and the recalculated output, and the largest difference is for the TEAS disdrometer. But for this day, the differences are quite small and within the measurement error of the rain gauge. And the differences in these results, they sort of tell us that in rain studies, one needs a lot of rainy days to draw firm conclusions on instrumental accuracy, simply because there is a large spatial heterogeneity and all instruments are affected by different droplets. But luckily, we have a lot of rain events. In fact, the summer of 2023 was the wettest in 12 years in Denmark. We had a drought early in the summer, but then everything changed. So that was it for me. So thank you very much for listening.
Well, thank you very much, Ebba. That was really enlightening. And it's really interesting to hear you have a lot of data in rain after all. So that's great. Okay, for the next one, we have Iván Prada, who is going to talk us about PLOCAN, the experimental campaign at PLOCAN. So, Iván, the floor is yours.
Hello, everybody. Can you hear me? Is it good? The sound is good? Okay. Let me just 1 moment share my screen. Okay. Well, thank you for the opportunity to introduce. I'm Iván Prada. I'm a project manager and innovation manager here at PLOCAN. I will be the one that we will go through our experimental campaigns we're doing during the AIRE project. In my presentation, I will first go through what is PLOCAN, just to give a brief hint of what we do and what is our role in the project. Then I will try to introduce the airborne dust, what we call Kalima events here in the Canary Islands, and what is their influence and why I think they're relevant for the wind. Afterwards, I will give an explanation of what the sensors that we have deployed and what are we are gathering here in our test site regarding these Kalima events and also meteorological data. And also I will make a brief introduction of the wind experimental turbine that is not ours. It's a wind turbine that is on a European project. This belongs to another company, but we have an agreement to use the data in this project. And afterwards, finally, I will give a brief explanation of the future blade inspections that we're going to undertake in the project. First of all, I just want to make a very brief introduction of what PLOCAN is. PLOCAN is a public entity funded by the national government and the regional government of the Canary Islands. The main mission of PLOCAN is to operate a set of observation and infrastructure for the services, the research and development of in the marine environment. We hold a test site, a 23 kilometers square test site of open ocean in the northeast of the Gran Canaria Island, in the Canary Islands, Spain, the outermost region. Within this test site, we have an offshore platform. It's capable of hosting 15 people during 15 days if this is requested to perform research. We also have a fleet of unmanaged vehicles for marine observation. We have vessels. We also have electrical infrastructure for the connection of different energy prototypes to the island grid. And we provide services related to these infrastructures, housing prototypes, access to the offshore platform and the sensors and data gathering equipment that we have there. We also provide coastal and marine observation services. We provide support in the logistical and operation required for demonstration projects or research projects. And we also give meteorological and oceanographic data services and special training and coaching. Well, getting into the matter, we are as a position to the rest of the partners. We don't have a high or very big precipitation of rain. We are a subtropical region. We are under the influence of the anticyclone of the Azores, so we have a stable temperature and low precipitation during almost all the year. However, this trade winds is from the northeast. When it changes and it comes from the southeast, we can experiment what it calls a Kalima, is the airborne dust in the atmosphere. When the wind blows Saharan dust to the Canary Islands, as you can see in this image. Just to make a hint, when the particle measurements of 10 micrometers is above, I think, 50 grams per meter cubic, it's considered that the Kalima is present. As I said, the Kalima is related to the different deserts. It's not only one thing that we suffer here in the Canary Islands. Every desert in the world suffers in some extent this event. And as the projections of expansion of aridity in the regions surrounding these deserts goes on, we will see that these events will probably be more common in different regions. In the last year, 2022, the effect of this Kalima was pretty wide around the subtropical region, but we also experiment some events. In March 2022, for example, there was a very heavy, very extreme Kalima event that could be seen in the mainland, and it reached even Austria, because there was a vertical Kalima that reached 4.5 kilometers. So this is not something that's only relevant for us. It might be relevant in the future, as we take into account that the renewable resources for wind is located all around the world, and there's a lot of resources in the subtropical region and other regions that are subject to this Kalima event. Well, here at PLOCAN, we are the leaders of the task 2.4 related to the data collection of subtropical climate. In this task, we are going to have 4 main assets. The first asset that was installed within the framework of this project was an air quality station. It was installed in our offshore platform. As you can see, the offshore platform is around 700 meters from the experimental turbine that we're going to get data also from. I will talk more about these sensors in the next slides. I just want to make a brief hint of what we have, what assets we have for this project. We also have in this offshore platform a LIDAR, a laser beam instrument that provides wind profile. We have a meteorological station, and also, as I mentioned, we will want to have access to the turbine SCADA data from the experimental turbine. Well, the first sensor that we got into the platform in the frame of this project was an air quality station. It's a Kunak brand AIRE Pro wireless model. It was installed in April this year, and it's sampling an average hourly. It can sensor particle from 1 micrometer to 10 micrometers, and it also provides additional information regarding the presence of other pollutants in the air, like carbon monoxide, nitrogen, ozone, and sulfur dioxide. It also has an integrated temperature, pressure, and relative humidity sensor, and it also incorporates a mechanical anemometer that is installed in the same height as the meteorological at the air quality station in order to gather information regarding the wind. Since it has been working, we can see that it's comparison with the already stated data from the regional government stations. We can see that the sensor is working well, and it has already registered an event of Kalima, a very severe event that occurred in October. In this event, there was a few days of a very heavy Kalima. It was capable to see, as you can see in the video, it was seen through the space, and it was well registered by the sensor. It also provides information ongoing. We haven't got any issue with it since it was installed. And we have information regarding humidity, temperature, wind speed average, and another information that is made available in the repository of the project. Another of the assets we have for the project is a LiDAR. It's a LiDAR model ZX300M. It was installed last year in June, and it's been working until today. It provides an average 1 second and an average 10-minute information data. It provides information regarding vertical wind speed, horizontal wind speed, and wind direction in different heights. It's configured to provide information of these 3 parameters from 20 to 160 meters, taking into account that it's not installed at sea level. So we have to take into account that it's installed in the terrace level of the platform. So it's 24 meters above the sea level, more or less. And since it was installed, we have done a measurement of the available resource at the test site. We have finding that if we take into account the wind turbine, the experimental wind turbine that is placed in the test site, we can see that we have 2,250 kilowatt hours of wind resource. And regarding the direction of the wind, as I said, the predominant wind is northeast. It's the one that is the trade wind from the Azores anticyclone. And this is not anything that is surprising. You can see that we also have some periods where the wind comes from southeast. In these periods, when the wind from the Sahara is powerful enough, we experiment this Kalima. We complement this information with a meteorological station. This is a Vaisala meteorological station model WXT530 that measures quite a big range of parameters. We can measure rain. It's useless here. We don't have enough rain to be taken into account. But we have UV radiation, wind direction, wind speed, humidity, air temperature, and pressure. Some examples of the last data that we have gathered from this meteorological station. You can see in the image, we can see that the wind direction is pretty consistent through time. We have also the wind speed is more or less what we expected. The humidity, the pressure, and the air temperature are completely what is expected. We also have access to an experimental wind turbine. This is owned by a Spanish company, Steico. We have an agreement with them to provide us data from this, the SCADA data and the meteorological equipment they have in the wind turbine. We are at the moment negotiating with them the way to share this information. We still have to see if this information will be available openly to the repository or if we could only use it inside the project. This is something that we are working with them. And we have started to recall some of this information. We are working with them because we have seen some anomalies that we need to make sure that is correct before we share with the project. I hope that within the next month, this information will be available for the project. And finally, I wanted to speak about the future inspection from the blades that we are going to do. We're going to do it in two ways with a replication resin. This is a high precision resin that is used to characterize the deposition of, or will be used to characterize the deposition of sand in the blades with a precision up to 0.1 microns. And also we will take high resolution images through the use of drones. It's a very complex campaign because there are a lot of factors that have to collide. We need the ocean to have the conditions for the boat to get to the wind turbine. We need the wind to blow as little as to make it possible for the vertical works. We need also that the technical people from the wind turbine are available to lock the turbine for its security reasons. So we are planning ideally to have 4 campaigns during the year. One first campaign will be before any event of Kalima has been in place, so we can just make a characterization of the blades, and we'll try to go every time a Kalima event is occurring in the test site to see how the deposition is. And we also want to see how the performance of the turbine is affected by the Kalima event, if it's relevant or not. And that's all from my side. That's what I want to present. Thank you very much.
Perfect. Thank you very much. It was really interesting. Great images. I really like to see how everything is going on over there. So for the next one, we will have Peter from OREC Catapult. He will show the experimental campaign at OREC. So Peter, the floor is yours.
Sure. Thank you, Estefania. I will share my screen. Yeah, hi everyone. I'm Peter Kinsley, part of the materials team at ORE Catapult, and this is our experimental campaign for our offshore wind turbine. So for those of you who don't know who Offshore Renewable Energy Catapult are or what a catapult is, we're a network of 9 world-leading technology innovation centres for a range of important industries, as you can see bottom right, with a mission to deliver growth and innovation to UK companies within these sectors. So this is quite similar to the Fraunhofer Institute that they have in Germany. So at ORE Catapult, Offshore Renewable Energy Catapult, we are dedicated to wind, wave and tidal energy. So we do this by working between academia and industry, where we will improve the commercial viability of products that are coming out of academia through research, testing and validation. And then this loop is kind of completed by feeding back what industry wants back to the foundations of academia. So we have 8 UK regional centres. A lot of these are offices, but we have a floating offshore wind test facility in Aberdeen. We have an 100-metre blade testing facility in Alaiz, along with drive train testing and a blade erosion test rig. And then finally in Fife, we have our 7-megawatt Levenmouth demonstrator turbine, which is top right, as you can see in the red box. Sorry, I think I just muted myself. All right, so this is Levenmouth to the left. So it's the world's most advanced open access offshore wind turbine that is dedicated to R&D. It has a walkway out to it, which makes it quite attractive for people coming to test and validate. But it does get mainly offshore wind conditions, which has given it its accreditation as an offshore wind turbine. So it has 800 plus sensors, which has made it very useful for running trials, which we have done commercially and within our own research. As you can see, through leading edge erosion, drone trials, blade crawlers, and just overall characterization. So this includes our work in AIRE as well. I keep muting myself somehow. Okay, so these are the LDT characteristics. So at its rated wind speed of 10.9 meters per second, it can reach quite aggressive tip speeds of 95 meters per second, making it obviously an ideal site for running leading edge protection trials for leading edge erosion, as we're doing now and as we have done since 2021. So this site experiences around 625 millimeters per year in rainfall, with intensities reaching up to 95 millimeters per hour. And to the right, you can see the windroses that were averaged for each month between 2015 and 2018. And this averages out a wind speed of 9.41 meters per second, coming, as you can see, predominantly from the southwest. So why are we collaborating within AIRE? We have a lot of knowledge and experience gained through commercial projects that have utilised our assets, including the blade erosion test rig, weathering and LDT. So these are mainly around leading edge erosion, and I've listed a couple of these projects off. So this, these research capabilities synergize quite nicely with AIRE and its objective of decreasing blade operational and maintenance costs, and it's a good opportunity for strengthening European collaboration. So this is what we will be researching within AIRE. To the left, you can see within Work Package 2 is the unique set of offshore environmental data, which is what I'll be describing in this presentation a little bit further. In the middle of Work Package 3, we'll be validating a lifetime prediction model, which will use this environmental data, and will use data from our blade erosion test rig on a certain material. And then we'll validate this against inspection data on the same material on the wind turbine. And then finally, in Work Package 6, we will complete a combined test methodology with rain erosion and UV and natural weathering as well. All right, so that leads us to our measurement campaigns. So this is our site layout on the right. You can see our met mast to the left, which actually isn't there anymore. It's been decommissioned as of October last month. And the turbine to the right. I think most people know what comes out of SCADA and met mast data, so I won't list those off. But there's 616 sensors that come out of it, and I've put a link to our pod, which is where you can access this freely. It has to be requested. So yeah. Onto the distrometer. Hopefully most people know what a distrometer is by this point. So we have a PWS 100 located at ground level. And again, this is very similar to the distrometer that Ebba described in her presentation, but it has some advantages, such as being able to cope with extreme conditions where it won't corrode, and it has been shown to have quite high accuracy. And I've just included a little example of the kind of data that comes out of that. This is actually at our site at NOAA, which is, again, another offshore site that we have. So this is used, well, the LDT dataset will be used for the lifetime predictions that I talked about in Work Package 3. Okay, onto the LiDAR campaign. So we had 3 main objectives for our LiDAR campaign that were conceptualized and turned into actual campaigns with support from Woods Group, who also own and operate the LiDARs. As you can see, there are some quite powerful LiDARs at 4,000 and 6,000 meters in range. So we had the first one. We wanted to characterize horizontal wind speeds up to 2 kilometers in altitude. Very ambitious. And we plan on doing this with a G4000, which is positioned at, well, I say met mast, where the met mast was. The second objective was to capture inflow wind velocity at the blade tip to study potential impingement characteristics of droplets onto the leading edge. And to do this, we'd have a G4000, Galleon G4000 positioned at the met mast. Again, I'll go into these in a little bit more detail. The third aim was to capture wind inflow and wakes on LDT, and that would be a Galleon G6000 positioned on the nacelle, scanning both forwards and backwards. So this is the first objective in the first campaign, to scan at 2 kilometers in altitude. The campaign will use a VAD scan, and you can see on the table on the left are the range gates. So we have a higher density of range gates between 0 and 500 meters, which is where the data will most likely be a lot more available. The plan is, if we can't scan to 2,000 meters, then we will reduce this, which is done quite easily. So on the right, you can see the radius of that VAD scan up at 2,000 meters, which equals 932 meters. The second LiDAR campaign is the impingement characteristics, which will be a vertical arc scan or a range height indicator, RHI, which is measuring as close to the rotor plane as possible. You can see on the top two images that it's slightly off kilter to the tower, so that we can only look at and analyze the points at which the LEP or the leading edge protection actually is, which is towards the end of the blade. And this also avoids the hard target return that you'd get from the tower. So because we have predominantly southwesterly winds, it makes this campaign quite good, because the wind turbine will be facing the LiDAR positioned at the met mast or where the met mast was. And finally, the nacelle-mounted LiDAR, which will be performing 2 horizontal arc scans or plan position indicators, PPI scans. And we have a higher density of beams facing downwind, 11 beams compared to 5, which gives an increased resolution for the more complicated wake patterns that will be occurring. And this will be around 10.2 rotor diameters away from the wind turbine. All right, so that leads me to the last piece of instrument, which is the pyranometer, the Huxiflux. And apologies if I've completely butchered that pronunciation. It's a Class A pyranometer that is heated to prevent moisture buildup. And it will be used to correlate UV data at Levenmouth with our combined UV and rain erosion test methodology. So it will inform what settings to put our QSUN, which is the UV accelerated test rig, to. So that kind of concludes our measurement campaign, which should make LDT one of the best characterized offshore wind turbines in the world. So if anyone has any questions and they'd like to get in touch, please feel free to reach out to either myself or Kirsten Dyer. Thank you.
Okay, perfect. Thank you very much. It's an enlightening presentation. Okay, so right now everybody it's muted and they cannot share their camera, but we're gonna start with a Q&A session. So if anyone has any questions, just put the hands up and I'll give you the opportunity to open the microphone and the camera. We have, if Ebba, Iván, Oscar, and Peter, you can put your cameras in case they want to address the questions to you directly. It will be good for us to see everyone's faces, and also it will be a great image to put on our social media afterwards. So for now, we are open for Q&A. If anyone has any questions, please raise your hand, and yeah, well, the floor is all yours. Okay, Johannes. You have the mic.
Hi, good afternoon. Can you hear me?
Right. Yes.
Okay, I have a question for Peter. I was curious to know what your probe volume is of the LiDAR, the vertical scanner that's pointing towards the turbine, at the point where it reaches just in front of the turbine.
So is that asking at what distance it will be measuring from the blade?
the actual probe volume that you're sampling at that measurement point. I mean, you don't measure point-wise; you have kind of a volume averaging, right? Curious to know how big the probe volume is at that point.
Yeah, good question. I can't say I'm a LiDAR expert. It was Wood Group who supported us with this quite a lot, so I will ask them and get back to you, Johannes, if that's okay.
Thank you.
anyone else in the group has any other question? Come on, don't be shy. Okay.
Maybe just a general question to all the presenters. There was this issue we discussed earlier on in a project about measuring wind speed at the same time as measuring rain. Has anyone made any progress in this regard to know, so we can kind of investigate what is the effect of rain on the wind speed measurements, especially at increasing rain rates, I guess?
Well, I showed some plots, just that the availability doesn't seem to go down much. But then I've also looked at the example wind profiles when it is raining, and I think like we will take more analysis, but so far I would say it looks pretty good.
So you don't expect a shift in the actual kind of calibration curves that one needs for the LiDAR because of the presence of rain?
My impression is that the LiDAR filters it out quite well.
Okay, that's good news.
The LiDAR should see a double Doppler peak and be able to distinguish, but I don't want to put my head on the block for this statement, but what I've seen so far, I think looks quite promising.
Okay, this is good news. Thank you.
Iván, you also wanted to share something on the matter? Oh, sorry.
No, in my case, we don't have almost any precipitation regarding rain, so we don't have suffered that problem here in the Canary Islands. It's anecdotal that we have suffered that.
Iván, I actually had a question for you because you showed your relative humidities and you said they were quite standard. It was some 60 to 70%. And I thought, oh, that's really low for an offshore site, but maybe it isn't. Would you say that's, you get such dry airs?
I'm not an meteorological expert, so I was told by our data that was okay. However, as we have this trade mean, we usually don't have a lot of humidity.
Yeah.
It might be that it should not be so dry regarding that it's offshore, but it also might happen that it's as it is not in the sea level, it's around 24 to 30 meters.
Yeah.
Maybe the wind that it's going through is quite dry. I can, if you have interest, I can ask.
Yeah, I trust your data. I was just surprised. I would have thought it would be higher. But it's
okay. Now I'm curious. Now I will find out.
That's good.
Now I don't trust
something definitely to discuss in the next General Assembly.
Yeah.
Okay. Is there any other question around the group? Well, okay. Well, I'm glad to announce that this is the end of our first webinar of AIRE Project. Thank you very much for all. Thank you everyone for your time and to be here and get interested in our project. We're really excited about it. And keep in touch. Please follow us in our social media. Check out our web page. And we'll soon have much more events coming up. So we will keep in touch. Just a reminder to everyone, this was recorded. I know we cannot hear you or we can see you, but like eventually we'll have this available for you to also revisit anytime you would like. Francesco is asking if it's possible to share the slides. Yeah, we can also have them available. If I can put them in our website. We'll make a post webinar blog, and in there, make sure you can have access to this kind of information. Okay, well, thank you very much to everyone, and hope to see you soon.
Bye. Thank you.
Bye bye.
Bye. Bye.
Charlotte has a hand. Or was
It's like waiting, I think. Yeah.
Hi.
Hi.